decision making, and that's what we will call this as dynamic optimization. Basically, we take decisions dynamically. So it's a sequence of steps that we follow. We make decisions, we get information, we make decisions, and so on, right? So this is the framework. And then we saw some applications. There are wide ranging applications of dynamic optimization. So sequential decision making problem, I have given introduction to these. So what are sequential decision making problem? We take decisions, we get information, we get decisions, and so on. Now obviously how we represent the information that will arrive in future and how to make decisions. So in this course we want to formulate all these things in a nice way. So the goal of the course is to model sequential decision making problems and make effective decisions in the presence of uncertainty as well. Because if there is no uncertainty, then you may kind of hard code it. Okay, so if things are very deterministic and feasible, then you can code this in a tabular way. The table, like rows and columns, are finite, and then you know the set of actions that you are supposed to take, and then the search space is limited, so you can make a number of cases in your code, and then you solve the problem algorithmically. But the whole challenge is that the search space can be very big. So as I keep saying, it's like playing the game of chess. There are so many possibilities, so many configurations of the board. So basically, it's not at all possible to write down all possible cases. Okay, so this is where we get into this area where we need to model the problem. We need to do pattern matching, prediction, and so on. So neural networks will help in these things. Okay, so we have seen this. Now let us now do the real stuff. We will formulate the problems. Now sequential decision making problem could be classified into two major classes. Let's say finite horizon problem and infinite horizon problem. Finite horizon problem further could be classified as deterministic and stochastic, and then infinite horizon problem could also be further classified into deterministic and stochastic. Of course, here there are further classes. There are cases where you have fully observable case. There are cases where you have partial observations, POMDP, and so on. So, but broadly, we have these two classes, and then we will classify them further as we go along. So, so we will start with something called deterministic optimization problem. So finite horizon and deterministic. Okay, so that's our starting point, and then we will gradually make it stochastic, and we will go into infinite horizon case. So today this is our plan to formulate finite horizon problems. And so what are finite horizon problems? As the name suggests, it's about some limit, let's say, in time or steps. Okay, so it depends what we are talking about. So in words, we can define finite horizon problems now as those where decision making process has finite or fixed time or number of steps t. This means that the agent's goal is to optimize its performance over its predefined finite time horizon. Okay, so that's in words, but we will formulate these things. Now, example of finite horizon problems. One possibility is robot navigation in limited time. Task here is a robot is supposed to kind of navigate the maze. Maze could be like complex, but the real life environment could also be like a maze. You have roads and you have to follow the path and so on. You have certain obstacles, traffic lights and things like that. So anyhow, so in this figure we can see a robot delivering something, and so this could be seen as finite horizon problem, because the robot has to satisfy certain objectives in some finite amount of time. The item has to be delivered. Okay, so that's could be seen as finite horizon problem. Okay, if it takes too long, the it's essentially like the job is not done. So this could be a real life example. Now, if you play a video game, then usually video games also come with some fixed levels. So you play level 1, then they tell you that okay, you unlock level 2, and then you keep playing and so on, and then eventually you kind of keep going, and then ultimately there also you have certain terminal step where you will reach an expert stage, and then you say that okay, that's the final level. So so this could be seen as a finite horizon problem again. It could be a portfolio management problem, could be seen as a finite horizon problem. An agent, whoever the agent, if you are rich enough, then you can hire some agent who will do the portfolio management for you, assuming that you are so rich that now you need someone to manage your portfolio. And basically portfolio management is about managing your resources. Basically investment plans, it may be trading in stocks, real estate, buying some assets like gold, buying villas, flats or land, so many things, right? So how do you kind of diversify your portfolio? And this could also be seen as a finite horizon. So basically you, or let's say if you go into a very narrow area like stocks and so on, then you may say that okay, within certain days you expect certain returns and so on. So you may formulate this as a finite horizon problem. You have a target of 5 years, and from within 5 years, so that's your time horizon, which is like finite 5 years, and within those 5 years you want to kind of increase your profit, or you kind of buy or sell your stocks in a way that you overall stock value is like more than what you invested. So this could be formulated as finite horizon problem. So how do we formulate such problem? In a finite horizon problem, basically you have states denoted by x naught. So this is where I will use the notation x naught for state. So you start from somewhere, you start from state x naught, and then x1, then x2, and so on. And let's say you reach a state xk, and so a arbitrary step xk is being used here, that you will be at some point xk, and then at an arbitrary point xk you're supposed to take some decision, let's say, or action you will take, or these are synonymous. Okay, so the decision you will take, or the action you will take, or the control you will take. So depending on the application or the area, these things are defined in a different way. But as I said, one of the thing in this course will be that we will unify these ideas. So control theory, people use control, but it could be action, or it could be some decision. Or so so you are at state xk, and you will takes some control. So obviously the possibilities you have for the control will be many. So that's where the problem becomes interesting. If someone gives you only one option at a time, then obviously there is not much to do. Okay, so so this is the control, but there will be multiple possibilities of control, and you will pick one of those. So let's say arbitrarily you pick UK, and you will pay a cost for that. So at state xk, you took control UK, and the cost of that going from xk to xk plus 1 is denoted by gk. Okay, so this is the stage k problem, and obviously there are future stages. So we will go, and this will be kind of recursive now. So same thing now, just the indices change from k to k plus 1, go from xk plus 1 to xk plus 2, and so on. Okay, and this is a finite horizon problem. So here capital N is finite. So basically we want to terminate by then. The finite horizon will also include something which may terminate early also if your reward is satisfied. So basically it terminates in finite number of steps. So so this is the finite horizon and deterministic. Deterministic in the sense that the controls that you will take and the state you have, the gk will produce something which is deterministic, which is xk plus 1. Okay, so there is no stochasticity right now introduced here. For a fixed uk and xk, you surely go to xk plus 1 in a deterministic sense. So this is the basic form, which we will keep modifying, updating, and so on. But this is the picture we have in mind. This is a sequential decision-making problem. That's why you see this sequence of states x0, x1, and so on. Okay, so in finite horizon problem, the system evolves over a finite number n of time steps, or also called stages. The state and control at time k of the system will be generally denoted by xk uk. So throughout we will use this notation, xk for the state and uk for the control. In deterministic systems, xk plus 1 is generated non-randomly. So xk plus 1 is solely determined by xk and uk. Okay, so there is no randomness involved. So we will get into the stochastic case, but xk plus 1 will be produced deterministic way from xk and uk. Okay, so this is more or less the setup of finite horizon deterministic problem. Now let us introduce key concepts here. So furthermore, we can write down the states that we produce xk plus 1 as a function of the state xk and the control that we took. Okay, and so this fk is changing as well. So it's not necessary that your function fk at the kth step, which tells you how to go to the stage k plus 1, is not necessarily the function itself is not necessarily fixed. Okay, so that itself may change. It does not have to be a continuous function also. Okay, so this fk, we will see that it will be depending on the problem at hand, we will change this. A simple thing would be a lookup table or so on, right? But there is a lot we can do here. Some kind of pattern matching might help here. Okay, some kind of neural network might help us in figuring out the next step, the next state. Okay, so for the moment we keep it in this form, and we do this obviously for n minus 1 step. So now here k is the time index, that's clear. Xk is the state of the system, an element of some state space, And UK is the control or the decision variable that I have said already, to be selected at time k from the given set UKXK. So as I said, the control that you get UK at stage k comes from many possibilities could be there for the control, and you will pick one of them. Okay, so basically at stage k you will have a set of controls to be considered at stage k, and then you go to the next stage, and then you have set of controls UK plus 1, XK plus 1, and so on. So and Fk is a function of xk uk that describes the mechanism by which the state is updated from time k to k plus 1. So obviously we might call this we will describe this in a more concrete way when we introduce policy and so on. But this is a way to transition from k to k plus 1, obviously. So n is the horizon that we already discussed. Okay, so for finite number of states, the system function Fk may be represented by a table, as I said, that gives us the next state xk plus 1. So if there are finite number of states or reasonably finite, like finite also may come in like you don't want to have a very big table of billions of rows or columns, right? So finite here means reasonable size table. Then Fk may be represented by some table. So but in otherwise it may be some kind of a function or some kind of a implementation which we will make it precise. So this Fk really depends on the problem at hand. We can formally define state space as the set of all possible xk will be called state space at time k, and it can be any set and may depend on k. Control space also we can define as set of all controls uk at time k. So we can write down finite horizon problems as some transition graph. So really how the finite horizon problem will look like will be like this graph, and this graph has some start states or the initial states, and then it will have some terminal states. So if you know a bit about graph, or then you may think of these as some source and then terminal state. Okay, or if you may have done some automata also, there also you discuss these transition tables. So at stage 0, obviously it's denoted by x0. These initial states could also kind of start from many possibilities, right? So let us say we start from x naught here, and then we have multiple possibilities to go to x1 from x naught. So these are the possible controls. Let's say u0, u1, u2, and u3, let's say. So different controls will lead you to different stages. So here x naught, if I take control u naught, then I will go to this node here. Okay, and once I am at this node, then again I have two controls possible, and if I take this control, then I am at x2 and so on. Okay, so the way I get to x2 is given by f1, x1, and u1, obviously. Okay, so as you can see from the graph, it can be a really very big graph. Okay, if the possibilities each time kind of keeps in some number, then it will, for every initial state, let's say you have 4 options, then for the next node you have another 4 options, and so on. So as you can see, it's kind of grows. It can really grow very fast. And So obviously your goal to solve a problem is to go optimally from x naught or the initial state to the terminal state, and here the optimality will be defined via the total cost that you will pay to go from initial state to the terminal state. So, so obviously we have to figure out the cost as well. So this is the transient graph for the deterministic finite state system. Nodes correspond to state xk, arcs, the edges will be denoted by xk uk pair, and an arc obviously has a start and end node, and the cost is in general denoted by gk, xk, uk, and this could be seen as the length of this arc or the edge weight that you know, and the problem is equivalent to finding shortest path from initial node x0 to the terminal node t. Okay, so here the shortest path is like the sum of the edge weights are minimum. Okay, so we can have this graph view for sequential decision making problems. So let us look at the cost now. How do we write down this cost? So this is our system. Xk plus 1 is obtained from fk, xk, uk, and the cost function will add up obviously. So we have the terminal cost, which is gn xn. So at the last step, how did I reach xn? So that we separated out, and the remaining ones could be written kind of recursively. So since only the last one is a bit different, so we keep it a bit separate, but other ones can be recursively kind of, I mean it's the same expression, just the k changes indices. So we can write this in this way. We start from 0 to n minus 1. So obviously here we have added up the cost. That's the total cost obviously. So for a given initial state x naught, what we are supposed to do is to minimize this cost over control sequences u0 up to un minus 1. Okay, so in this we have taken a set of controls starting from u1, then we took u2, then we took u3, and so on up to un, okay, un minus 1. So obviously the cost depends on the controls that we took. So now the whole problem is about what could have been the minimum cost, which translates to what could have been my optimal controls, because my controls decided where I will go in the next state, and that decided the cost. So basically this whole cost could be seen as a minimization problem over control. Okay, so which choices of the control I would have taken so that this total cost is minimized. So this is an optimization problem over the control sequences u0 to un minus 1. So if we can minimize this optimization problem, this is our cost. So we are supposed to minimize this over the controls. So this is how we have written this: minimize the cost over the controls u. So as I said, uk that you choose is coming from the set of all possible controls available at k, okay, xk. So maybe there is a small typo here. I should have written it xk, x sub k, and you do this for all the uk's, right? So 0 to n minus 1. So this is basically an optimization problem. Okay, so this is our formulation of the problem. So how do we calculate the cost? That's the whole thing, right? So I want to solve a problem, and for a sequential decision making problem, I have sequence of steps, and I know the cost that I incur when I choose the controls. So what are the ways we can calculate the cost? One possibility is something similar that you have seen if you have done some algorithm course, then you know something called dynamic programming, and there are like quite a few classes of algorithms. You study like greedy algorithms, dynamic programming, and then there are like a few other. So one of the ways where we will calculate the cost will be similar to what we see in dynamic programming. So sequential decision making problem is essentially a, to a large extent, boils down to this quote that we see here: life can only be understood backwards but must be lived forwards. So this is more or less will be the key throughout this course. Actually, you will evaluate because you will be building a learning agent that will learn. Basically, it's not a static agent. So the agent will keep learning also throughout. It never ends. Just like you living in this real world, you keep learning and keep improving your decision making. Okay, or more technical would be like policy, right? So you will, until now, you will see what are the steps you have taken, the decisions you made. Maybe you will learn from the experience, and you will also learn from external experience of someone, some of your peers, like alumni, what they did, can you follow similar path, and so on. But overall, you are also looking at the life of your alumni in a backward way. What they will do in future, you don't know yourself. So you will analyze somebody else's life also in a backward way. So anyhow, you will analyze. You can analyze things like that. Okay. So what you have done and what you can correct in future if you are in a similar state. Okay. So this is basically about. This is the philosophy that more or less we have to do, or any intelligent agent has to do this learning and keep updating in a continuous way. So this is what we will do, because the real life is so complicated that you cannot really program specifically in advance. So some cost can be estimated by evaluating backwards, and in DP you see this in some examples. You see this, or so there is something called tail subproblem or recursion, if you're familiar with. So a nice problem to think about this is this problem. Okay, so there is a person who wants to climb the stairs, and the person wants to climb the stairs, but there is a rule that he can take one step at a time or two steps at a time. Okay, so basically he can go normally that we do, like one step, or he can jump a step. So basically 2 steps at a time. Okay, so and there are n stairs, let's say. Then the task is to count the number of ways that a person can reach at the top. Okay, so how do we solve problems like these, right? So how many ways could climb the stairs, right? The sequence could be like 1 1 1 1 1 n times, so that's one way, or it could be like 1 2 1 2, something like that. And depending on n is even or odd, you will stop at 1 or 2, or it could be 2 2 2 1 1 and so on. So as you can see, there are so many possibilities, right? You may apply permutation, combination, or things like that, but I want to develop a recursive thinking for this. So by recursive thinking, I mean like I want to go to the tail subproblem. Now I want to see what is happening at the end of the problem. Okay, rather than solving via PNC, can I decode this from the tail onwards? Okay, or is there a recursion in this problem? What is happening at the end of this problem? Okay, so at the end of this problem, we see that the person might be ending his work by taking one step, or the problem, or it could have terminated by taking two step, right? So the ending we know is only two possibilities. Either in this 1 2 1 1 something like this sequence, the ending could have been 1 or could have been 2, right? Now those sequences that ends with 1, they are very different sequences. They will never intersect with the sequences that end with 2, obviously, because the first one ends in 1 and the second one ends in 2. So the number of ways it will end in 1 will never be overlapping with the number of ways in which it will be ending in 2. And these are the only two ways to end. So the total number of ways will be the number of ways the person will end in 1, and plus the number of ways the person will end in 2. So if Tn is the number of ways the person ends in this problem, then it will be simply T of n minus 1 and T of n minus 2. That's it. Okay. So this is how we figured out. We went to the tail subproblem, which was right at the n minus 1 and n minus 2 level. So basically we moved one step back. I said, okay, from this will be like the n minus 1 problem, and then we went 2 step back. So this was like n minus 2 problem. Okay. So this problem actually tells us some ways of calculating the cost in the finite horizon problem also, and we will see with some examples there also. This is like not exactly in the framework of sequential decision making problem, but I just brought in to get a feeling for how sometimes a problem can be solved in a backward way. So this is a worked out example now. So with n equal to 1, there is only one way to climb the stair. N equals to 2, there are 2 ways. 4, then there are like 5 ways, and so on. So so this is what I said just now. The number of ways climbing n stairs is equal to ways of climbing n minus 1 stairs plus ways of climbing n minus 2 stairs. Okay. So and then so in DP there are like few other steps, like there are like overlapping subproblems. Like if I compute a Fibonacci, then it's obtained from the previous two, so it's like the same recurrence. So Fibonacci of 4 will be Fibonacci of 3 plus Fibonacci of 2. But then in DP there is also an idea that you identify the overlapping subproblems. You don't want to recompute the same thing that you did before. So if you have computed Fibonacci 2 before, then you should not really compute the Fibonacci 2 again. Okay, so these are the tricks that you employ when you solve a dynamic programming problem. Okay, so with this little bit of detour, now we can go back. So obviously in Fibonacci you might use a recursion stack, and that's the recursion inbuilt stack we have in the memory when you call a recursive function. So it builds its own stack, and it's basically the function called stack, and then that's the inbuilt stack. And then, or you can also do memorizations here. So you can build this small table basically, and then read out the values if it was computed before already. So these are like simple things to do to avoid excessive repeating computations that you might do. Anyway, so but let us come back now to finite horizon problem. And the idea that we learned from DP is that it is possible to compute the cost backwards. Okay, in some way, from the terminal tail subproblem onwards, we can estimate what was our total cost. And once we do that, then next time when we will take decisions or the controls, then in the online play basically, then our experience of computing the cost before over the set of actions will be useful when I will take actions later on again. So this is this is more or less the idea. So this is a scheduling problem which is like this. So again, like many problem could be formulated now, okay, with some constraints. Like this is a scheduling problem, but obviously a scheduling problem comes with some constraints. Like if there were no constraint, then maybe just random assignment will work. But then scheduling always is like you have to manage somehow, right? So there is a overlap. If you are scheduling a class, then there is like you cannot assign simultaneously 2 lectures in one class and so on. So obviously scheduling comes usually with some constraint on resources. This is a very simple example. Suppose that to produce a certain product, 4 operations must be performed on a given machine, and few things maybe can be done in kind of parallel in a person machine. So let's say you are building a car factory. Few things may be done simultaneously, but few things has to be done once something is done before it, and then you can use it to assemble something else and next. So there are some constraints, and there are a few things one can do in parallel. So let us assume that there are like this constraint problem like this. The operations are denoted by A, B, C, D. So you can think of these operations as A, B, C, D. We assume, so this is the constraint, okay. So we assume that the operation B can be performed only after operation A. So in this sequence, you see B cannot come before A. That's what it's trying to say, okay. So we assume that the operation B can be performed only after A. So you will see here wherever B appears, it's only after A. So B appears after A. Obviously some C happened, but B will never come before A. That's what it's trying to say, okay. So B never comes before A. So B came after A, okay. So this first constraint is satisfied, which gives us this possible state, but actually there is one more constraint which says that an operation D can be performed only after operation C has been performed. So then C must come only after D, or I mean D can come only after C, okay. That's what it's saying. So D can come after C, cannot come before C. So as we can verify from here, D comes only after C has happened. So D comes after C has happened. So D comes only after C has happened. So in this you will see that these are the possible terminal states, okay, in this scheduling problem. These are the possible terminal states, all possible terminal states that you can get, okay. So the cost, like one possibility of the cost could be like SA, like the starting cost, starting from A. So that's, let's say it's SA cost, just leaving the initial state. Let's say it is SA or SC, or then we have a cost to go from A to C, okay. So AC, the cost for AC, like here it's showing like one possibility, right. So CAC and CCD and CDB, okay. So if you think of in terms of graph, then this you can think of these as weights and being added along this, okay. So this is just a one possible cost, but then your other cost could be SA plus CAB plus CBC plus CCD, right. So there are like multiple costs here, and what you are trying to say is like obviously the minimal cost, okay. If the problem is about minimizing, then you are looking for minimal cost that you will get, okay. So this is an example of a deterministic problem because it terminates in finite number of steps. Each choice of control leads to a uniquely determined state. So this is hence a deterministic problem as well. So for example, at state AC, the decision to perform operation D leads to state ACD with certainty, okay, and has cost CCD. Okay, so we saw deterministic finite horizon problem in the scheduling example. So that's like another example you saw where we can apply these ideas. Now I come back to the tail subproblem. I gave you a hint of dynamic programming, the stair problem, and how we can sometimes go right at the tail and look at the cost in a backward way. So here also, when we evaluate the cost, we can go from tail onwards. So you play chess and you lost. So obviously the tail here is that you I mean the cost is like at the end your cost is like too high in this case because you lost, and then we can do it for many other problems in the same way. So we would like to go from tail onwards. So what will be a tail subproblem? It depends. Tail subproblem may not be the last step. Okay, I mean we can think of tail subproblem starting from k. Okay, so k onwards. So k. So so tail subproblem in this case, let's say in this example, it's like xk star onwards. I consider that as tail. So if for example I know how to solve my tail subproblem, let's say in an optimal way, then I call it x star k, and that's my tail subproblem. So I put a star, meaning I from there onwards the kind of states I'm taking which are produced by the controls, they are all optimal. That's why you see star or everywhere. Okay, there is a star here, star here. So this means that there is a tail subproblem, and somehow I have figured out what are the optimal set of steps states to go from k onwards. Let's say I don't know much up to k, but k onwards I have somehow solved the problem. Okay, so then we will call this set of controls uk to n minus 1 as the optimal set of controls, and xk onwards as optimal set of states that we have. So so that's what I said. U star, wherever you see star, that stands for optimal. So this, in this case, u. So this is a control sequence, and this corresponds to the states u x1 star to xn star. Okay, so if I solve all my problem from start to end, if I solve the problem start to end, then it will be the optimal subproblem throughout. But if I know how to solve my problem from k onwards, then we will call it optimal tail subproblem. But here we are starting from 0 onwards, so we are like as if saying throughout. Okay, so from starting to the end these are the optimal sequences I got, and then these are the optimal set of states I got. Okay, so the tail subproblem is the one that starts at the kth step. That's what I said. Okay, so the tail subproblem we define as any. So k here is arbitrary again, and it minimizes over uk onwards. Okay, so this will be the cost for the tail subproblems. As you can see, the cost that we wrote before was for starting from 0 to n, but here we start from k plus 1 onwards, and we just separate out the current kth cost, and then remaining ones we write it in this recursive way, and then we also separate out the last terminal cost. So this terminal cost is just about like ending the task basically. Okay, so just like the initialization has some cost, you can think of terminating something has cost. Okay, and before that you were taking controls to reach certain state, but then you reach at n, and then ending the task has the cost gn xn. Okay, reaching there has cost, then ending the task there has the cost gn xn. So that's why we don't see any control here. Okay, so then the tail optimal control sequence, this is optimal for the tail subproblem. So that's what we say. If we can figure out these, then if we can solve this smaller problem, tail subproblem, optimally, if we can. Okay. So by solving, what do I mean? Basically, we will minimize this over all the controls that start from UK onward, just like the global optimization problem we had. We were minimizing over all U0 to UN, but here we said, okay, now first let me solve the tail sub problem that starts from K to N. So can you solve this smaller problem first? Okay, that's the thing. Can we solve this smaller tail sub problem? So principle of optimality, let U0 to UN minus 1 be an optimal control sequence. If indeed you can find an optimal control sequence, U0 to UN minus 1, together with X0, determine the corresponding states X1 to Xn star via the system, the original cost function. So consider the sub problem where we start at xk star at time k, and we wish to minimize the cost to go function from time k to n. So this is the case k tail sub problem. Then the truncated control sequence is optimal for this sub problem. Intuitively, it looks clear that I have a optimal control sequence from U0 to UN minus 1. Then if I take a subset of this, will it remain optimal for the tail sub problem? So intuitively it looks okay, yeah. I mean, if it can solve a big problem, why optimally, then why can't it solve a smaller sub problem where the subset is taken from this? Okay. So it's intuitively clear. We don't have to go into the proofs of all these things. So in words, the principle of optimality suggests that the optimal cost function can be constructed in a piecemeal fashion, going backwards. First, compute the optimal cost function for all tail subproblem involving the last stage, then solve the tail subproblem involving the last two stages, and continue in this manner until the optimal cost function for the entire problem could be solved. So this suggests that we can actually focus on the tail subproblems, okay, and go backwards. So if we look into this scheduling problem again, now, so this is the scheduling problem, and costs are given as weights here. Okay. So what is the cost, let's say, of initiating a task A from the initial state? Is cost is 5. Initiating a task C, the cost is 3. And then following up with the task B, the going from A will be 2, and making a task C after A will be 3, and so on. Okay. So this is the scheduling problem. Now the weights are given. So weights kind of give you the cost you have. So in this problem, how do I estimate the cost? Okay. So as I said, in some problems I can work out backwards, looking at the solving at the tail sub problems, and then see how it accumulates as a total cost. Okay. So this is what we are supposed to do here. So here the cost to go from AB to ABC is 6. So I'm now looking at the terminal, let's say. Okay. So what were the terminal cost involved? So from AB to ABC, the cost is 6. From this could be the terminal, the ending state cost. Okay. So these are the end GN XN costs, right? And these are the cost when I go from AB to ABC. Is cost is like 3. Okay, and this is just the cost of terminating the task. Okay, so GN XN thing, right? So so how do we calculate the cost here, right? So what is the optimal way of scheduling this, right? So one possibility is that, okay, I look at the terminal thing, and I optimize the terminal cost. I look at the terminal cost first. So if I look at the terminal cost first, then this guy seems to be smallest, like 1, and there is this guy also seems to be the smallest. Okay. And then I go to the next sub problem. So basically I will be here. So out of all these sub-problems, which one is the smallest? Okay. So here if I see this this branch, then the cost that I have is 6 plus 3 is 9. Now if I look at this, then 1 plus 4 is 5. If I look at this, then 6 plus 3 is 9. If I look at this, then 1 plus 2 is 3, 4 plus 3 is 7, and 3 plus 2 is 5. Okay. So then I've moved backward, and then I found which is the minimum cost, like so through which control I got the minimum cost, okay, or which is the minimum cost, or which control gave me the minimum cost at the tail sub problem. So in this case, what seems to be the minimal? This is like 9, 5. So and then this is 9, this is 3. So this seems to be the minimum so far out of all these possibilities. This seems to be the minimum. This is 3, right? And then we move backward again one more step, and then see what is the cost involved for each of these tail sub problems, right? So again you add the cost, you add the cost here, you add the cost here. So again you will figure out that this seems to be the optimal, okay? And then if you keep working backwards, then you will see that this seems to be the optimal, okay? So this is kind of trivial that we can do the cost calculation like that. So for this problem, this is what we have for this problem. So if so a stage 2 sub problem looks like this, and we are looking for a minimum here. So so we have already figured this out, and then stage 1 sub problem involves this, and out of this we are looking for minimization over all possible controls and so on, and then the final stage will be this, right? So that's the stage 0 sub problem where we have estimated the total cost, okay? So and we found out that this is the best possible decision to make, right? Okay. So as I said, these are simple problems, okay? But it's good for kind of like clarity, but the kind of problems we have to look at will be way more complex. Even in scheduling problem, if the number of products kind of like grows a lot, then you have to go for approximate cost computation, and that actually the approximate dynamic programming is the one that is needed in real life. So the whole challenge now is not this problem where the whole graph is given to you and the edges are given to you, edge weights are given to you. The real challenge is when even the whole graph is kind of like cannot be written down, or cannot be written down because it's too much for memory. We cannot really encode everything, and that's when things become interesting, because then it's not about exact cost computations, but it's about approximate cost computations, okay? And that is what in real life you will do. You will approximate the cost, okay? So so stage 0 problem is the entire problem. So that's clear, and the optimal value of stage 0 sub problem will be the optimal cost J star. So in our case, J star is known. So 2 plus 1 3 plus 4 7 plus 3 10. So this was our optimal cost. As I said, I keep repeating this. This is a synthetic artificial example where cost could be computed so easily. But the whole point of this course is that there are problems where this cost cannot be computed easily. Okay, that's where like we move away from the classical graph algorithm, shortest path algorithm, to very complex cases where you need tools from machine learning, pattern recognition, things like that, to estimate the cost. There is no such thing as like exact cost in real life. So this is where things become interesting. So now that my optimal cost is minimized, the j star is my optimal cost, and it got minimized over the set of controls. So in this case, the control was like which branch I took. So in this case, let us say controls are like, let's say it's a binary tree here in this case. So it's like left or right child. So let us say the below one is like the right child, and above one is the left child. Then the controls that you have is like L or R. Okay. So this you took R control, you took L control, you took L control, and then you arrive at the final state. So final state terminating the cost for terminating is 1. So you have minimized over these controls throughout the problem, right? So your U0 was L or R. So you choose R. Again you have the control. So in this case you have fixed set of controls. Again this is a simplification, right? But in real life you go to next stage, and then control set might be lot more, might be very narrow, very small range or small number of controls. You may have to take that step anyway, right? So you have no choice also sometimes. So this will vary the controls. In this case the controls you have are L or R, going left or right at each node. But that will be variable. The capital U set that you saw, the set of controls at point xk, that is a variable. That's why we use sub k for U sub k, right? So those are the generalizations. The control can vary. It cannot be just left or right thing. It may not be able. We may not be able to write this in a graphical way, because just the choices are so huge that it cannot be represented graphically. That's like another challenge. And obviously, as I said, there may be stochasticity. So you may have control, but then you also get some stochastic influence from outside as an external influence, and that will decide the possible controls you can take, and given the stochastic input, then you have to decide again. Okay. So in this production line, maybe some random influence can be incorporated again. So can your model learn this, right? So in this case, we have not considered any stochastic thing here. So but we will introduce all these things. Then we may have infinite horizon also. It's like we don't know when it will terminate. Okay? There are problems where we don't know, right? When there is no, like, we just keep going ahead, right? Accumulating rewards. So so the tail of an optimal sequence is optimal for the tail subproblem. So that's that we have seen. So solve all the tail subproblems of a given length using the solution of all tail subproblems of shorter time length. Okay, if you can build from the backwards, so you understand your life going backwards. Okay, so that's the point. So maybe you look at your most recent mistakes, and then the mistakes before that. So that's what it's saying here, that go from your tail subproblem onwards, solve the smaller problem, then, and you cannot neglect the you cannot neglect the other subtrees in this case. Okay, I mean, it's not like this is your minimum, so you will only look at this branch, but that may not be a good idea, because the cost that you incurred before may be very high. So actually you have to solve all, although it's showing here in yellow box that that this was minimum, so you will solve for this subtree, but then you also are looking at these. Okay, you are actually solving all. Okay, so you make a small subtree here, like this, and then you make a small subtree here, and then you make a subtree here. All subproblems have to be solved. Okay, just because this guy 1 is the least, you can say, okay, I found it, I will discard all others, and maybe my minimum cost will be just the branches that are coming to 1, and then I will just look at this subtree, which is CA onwards, and then I will look at only subtree with the root C. No, that is not what you are supposed to do. You are supposed to do for these guys also. Okay, because these cost higher up could be much lesser, so that the cumulative cost may happen that some branches have lesser. So in some way this is an exhaustive, I mean, you are not leaving out anything, right? So this is exhaustive cost calculation, although I am solving for the tail, but it is an exhaustive cost calculation. I am not leaving out anything. It's a optimal cost calculation and so on, right? But as I said, in real life, you won't be able to do it, right? So even here, if you want to compute the actual cost, you can see you have to do cost calculation for so many, right? So this branch, this branch, this branch, and then go to the higher tree, and then cost for this branch, and so on. So things can get really complicated. So this is one possibility, that we can go from tail subproblem onwards. So we can write down our algorithm like this one possibility, that where we solve tail onwards. So find out the optimal cost at the terminal, which is like Jn star, and then find out the minimum for a tail subproblem, which starts from let's say the k onwards. Okay, so you separate out the k cost, and then the k plus 1 onwards, the optimal is jk star. Okay, so if you can solve this for all the k, then obviously you have the total cost, which is j star x naught, which will be obtained at the last step. In our case, the last step is like going backwards. So we solve for n, then n minus 1 tail subproblem, the subtree that you saw, and then the bigger subtree, and then finally we have the cost j0 x0, which is the total optimal cost. Now once you do so dynamic optimization is indeed like a two-step process. Just again remember the quote, that you understand your life going backwards, but then you take moves, you have to take moves in a forward way, because for you cannot go back in time anyway. So DP algorithm is like that. The cost calculation is like backwards, and then knowing this cost that you have, now you can take optimal control sequences. So this is the DP where I am trying to understand the cost, which is backwards, and then the optimal control sequences that I will choose will be now like step by step from x0 to x1, and then so on. So then I'm looking at u0, the first step control, optimal control, what it will be. Then I am essentially minimizing over all these, and then I know a way what is my J1 optimal J1 star. I have calculated that. So this will help me choose the first control u0. Okay, so in when selecting the optimal control, I am going forward. I am starting from 0, and since I have optimal cost calculated, I know, okay, this is the control I should have taken, because I have the J1 star calculated, I have the J2 star calculated, I have Jn star calculated, all I have calculated. So this will help me select my controls now when I am actually doing the online play or the real life decision I'm taking, because I have some estimate of the cost that I did before. So this takes us to x1, obviously. So I know what is the optimal control now. So for the next step, and then I get to the next state x1 star, which is optimal. Then we can do it recursively for k equals to 2, k equals 3, and so on, and reach the end. Okay. So two stages, two steps. Computer cost approximation is one possibility, and then the forward is the actual decisions that you are going to take, okay, based on your cost or experience that you had from the cost calculation. So this is pretty much like the two-stage process, and this will be done again and again. And these are diagrams which will just kind of repeat, what we just said just now, that there are these tail sub problems, and then we are trying to solve this for each of these tail sub problems. So indeed, it graphically it is like a shortest path problem. So again, we are repeating the graph view. We have the nodes xk, which are the states, and then the controls xk, uk are the arcs. And the cost to optimize is the sum of the cost from initial to the final. And from the shortest path point of view, we are just kind of looking at the minimum cost. So problem is to find a minimum cost shortest path from the start node S to the terminal node T. Okay, so one easy or like very closely related example for shortest path is like the traveling salesman problem. So one may recall what is a traveling salesman problem. So here we are given n cities, and the travel time between each pair of cities, and we wish to find minimum time travel that visits each of these cities exactly once and returns to the start city. Okay, so this is basically the traveling salesman problem, if you can recall. So this is NP complete problem. So much of these is much of the practical algorithms that you will try to implement will be based on some form of heuristic, okay, especially if the number of cities are big. Okay, so because it belongs to this NP complete class, algorithms which will be heuristic and kind of gives you a decent solution to this problem, doesn't take too much time, that will be preferred in real life. Okay, you may not be like perfect, but you solve this in reasonable time, so that's like a good thing. Okay, so I think I will define this problem and then kind of not solve this, but then we will apply this problem, we will apply this DP idea of tail sub problem, and then how we can solve this problem in a DP way. So for the moment, I will just define this. So if you go by a brute force, then you may do all possible permutations of the cities that you want to visit. Okay, so all possible permutation of n cities will be like n factorial. So you go to one city, and then you have like n minus 1 choices for the second one, and then you have n minus 2 choices for the third one, and so on. So basically n factorial, and as you know, n factorial grows very fast. Okay, so this is indeed so brute force is clearly not a very good idea, and you have to go for some approximations. So if you go for a dynamic programming approach, it is O n squared 2 to the n. So basically it's exponential, so it's power of 2. Okay, so power of 2, so it's in the exponential class, it will grow very rapidly, right? 2 to the 70 or 80 is the number of atoms in the universe, roughly. So basically for n equals to 70 cities, your complexity is like 2 to the 80, which is like number of atoms in the universe. So this is how big things can be, right? Even this simple looking problem can be so. So I will stop with this small example. So we can think of this small problem where we will try to solve for this small problem. So where we want to visit cities A, B, C, D, and we assume that we can go from any city to any city. So basically it's like a complete graph. And obviously there are costs involved between cities because maybe some cities are very far, so you can think about the cost of travel. So that will be the edge weight and so on. So we will continue with this in the next class. Okay, so see you.